Here we have an RL circuit with a voltage V of t. I1 is the current in this loop here. I2 is the current in this second loop. Let's use Kirchhoff's voltage law in this first loop. Well, the potential difference across this inductor is the inductance of it, L1, times the derivative of this current with respect to time. Now what about the voltage across R2? Well, I1 is flowing clockwise in this loop, so the voltage across R2 for current I1 is I1 times R2. However, we have this current I2 flowing down the way through resistance R2, so that's in the negative direction as seen from this loop. Only clockwise currents in this loop are positive, give positive voltages. So this potential will be negative for I2. So we have I1 R2 minus I2 R2 as the potential across this resistor. So we can write it like this, and then we have I1 flowing through R1, so that's the voltage across the second resistor, and that must equal the voltage source V of t. For the second loop, I2 is flowing in the positive direction, that is clockwise through L2, so the voltage across it is L2 times the derivative of the current with respect to time, whereas the voltage across the resistor for current I2 is going to be I2 times R2, because I2 is flowing down in the positive direction for this loop, but I1 is flowing in the negative direction for this loop here, so we have to subtract off I1 R2, and the voltage source in this loop is 0. Now we are going to give some values to L1, L2, R1 and R2. L1 is 0.8 henries, L2 is 1 henry, R1 is 1.4 ohms and R2 is 1 ohm. We also have the initial conditions that both currents at time 0 are 0, and we are also assuming that the voltage source is a constant 100 volts, and as usual T is positive. So if we plug those values in, we get these two equations here. V of t, by the way, is 100. So the first equation here has been divided by 0.8. Now we let the Laplace transform of I1 be big I1, and the Laplace transform of little I2 is big I2. Now we have to get L of the derivative of I1 with respect to time. Just so as a reminder, that this is what we get. We get minus I1 at time 0 plus S times big I of S, but I1 at time 0 is 0, so we just have S times big I of S there, and here we'll get 3 times big I1 at S. So we get S times big I1 at S plus 3 times big I1 at S minus 1.25 times big I2 at S, and that must equal the Laplace transform of 1.25 times 100. Well, we just want the Laplace transform of 125. Well, 125 can be written as 125 times u of t. We can go to our table of transforms and look up L of u of t. We apply linearity here, take out the 125, so L of u of t is 1 over s, or we can just go and evaluate this integral. Since we're integrating from 0 to infinity, we're just dealing with a causal function for positive t, so that's why we can write 125 times u of t for 125. So anyway, that's our first equation. Here it is. And as for our second equation, well, for L of di2 dt is going to have the same form as for first derivative, the derivative of I1 with respect to time, of course. We just replace this with a 2, of course, and we know that I2 at 0 is also 0, so we get S times I2 of S. So there's the S times I2 of S, and then we have L of I2 here. That gives us 1 I2 of S, and then we have to get L of I1. Well, we write that as big I1 of S. So now we have these equations with the I1 terms appearing first and the I2 terms, and then the expressions on the right hand side not involving I1 or I2. So I'll use Cramer's rule to get I1 of S. So as we've seen in the previous video, the denominator is the determinant of the coefficients on the left hand side. So the I1 column is s plus 3 minus 1, and the I2 column is minus 1.25 s plus 1. Now as for the numerator, we take this determinant here and replace the I1 column with the expressions on the right hand side, 125 over s0, and the y or the I2 column stays as it is, minus 1.25 s plus 1. So let's get this determinant. We multiply 125 over s by s plus 1. And we subtract minus 1.25 times 0. Well, that's 0. Here we have s plus 3 by s plus 1. That's s squared plus s plus 3s. It's s squared plus 4s plus 3 minus 1 times minus 1.25. Well, that's going to give us minus 1.25. Now we can simplify the denominator a little bit and multiply above and below by s to get this here. Now this quadratic actually has factors. The factors of 1.75 are 1 half times 7 halves. That gives us 7 quarters, or 1 3/4. And here we get, for the middle term, we have 7 halves s plus 1 half s. That's 8 halves s, which is 4s. Now, since we have 3 linear factors in the denominator, we can write this as a sum of these 3 partial fractions where the numerators are just constants. And we have to determine what a, b and c are. Now the quickest way to do this is to use the cover-up method. So if you go to Wikipedia, you can look that up. Here is what we're dealing with actually. We can find that to find a, we just replace x, well s in our case, with this term here, little a. In all of this, except for this, we just cover up this x minus a factor. So we'll have LA squared plus MA plus N over A minus B times A minus C. So the first factor here has the form S minus 0. So we just look at this here, we just cover up S minus 0 and replace S in all of this with 0, and that will give us A. So we get 125 times 0 plus 1 over 0 plus a half times 0 plus 7 halves. That's going to give us half times 7 halves, or 7 quarters. Now as for B, we cover up this factor here and replace S in what's left with minus a half. So that's how we get B. If we go to the general situation here, we cover up x minus b and replace x in what's left of this expression with b. So remember, it's x minus b here. So here we have s minus minus a half, so we have to replace everything, all the s's here, with minus a half, except the s plus a half term. We just cover that up. So we get 125 times minus a half plus 1. Well, that's plus a half. And in the denominator we have minus a half for s, and that's multiplied by this here with s equal to minus a half. Minus a half plus 7 halves is 6 halves, or 3. Now we get on to c. So the denominator here is s minus minus 7 halves. So we cover this one up and we look at what's left. It's all of this here, and we replace s with minus 7 halves. So we've 125 times minus 7 halves plus 1. Well, minus 7 halves plus 1 is minus 7 halves plus 2 halves. That's minus 5 halves. So we've 125 times minus 5 halves. And in the denominator we've minus 5 halves, minus 7 halves here. Okay, we plug in minus 7 halves for s, and we've minus 7 halves plus a half. That's minus 6 halves, which is minus 3. By the way, these are 3 separate fractions, of course. I'm just writing down what a, b and c are. So this is a over s here, and this is the next fraction, and so on. So multiplying 4 by 125 gives us 500. 4 times 7 quarters is 7. The halves cancel here. Actually, we've minus halves cancelling here. Or sorry, no, we've plus half here, minus half, a half here, so we get a minus sign here. Okay, because we plugged minus a half in for s. So we've minus half plus 1, and we get plus a half on top, and we've minus a half underneath here. Multiply above and below by minus 2 here. This fraction on top. Now over here we should have minus 3, because we've minus 7 halves plus a half gives us minus 6 halves, which is minus 3. So these two minuses cancel, but we'll end up with a negative value. So we have 5 times 125 is 625 divided by 21. Okay, so here is I1 of s, and the inverse transform of this is quite straightforward. The first term involves 1 over s, and the inverse transform of 1 over s is just u of t, which is just 1, because we're just dealing with positive t here. So we have 500 over 7 times 1. And in this next one we have 1 over s plus a half. 1 over s plus a half is e to the minus a half t, or e to the minus t over 2. And then we have the constant minus 125 over 3 times it, using linearity. And for this term, has the same form here with a equal to 7 halves, so we get e to the minus 7 halves t, and the constant is minus 625 over 21. Alright, so that's I1 of s and its inverse transform to get little I1, the current in one of the loops. Now, we didn't get I2 of s, but we can use Cramer's rule again, of course. The denominator determinant is the same as for I1 of s, we just have to change the numerator. So, we replace the I2 column of the denominator determinant with the expressions on the right hand side. That's 125 over s 0, and the I1 column remains the same. So the denominator will be the same as before, but now the numerator is s plus 3 times 0, which is 0, minus 1 times 125 over s. That'll give us plus 125 over s on top. Now we saw the factors of this before, and we multiply above and below by s. So again, of course, we can use the cover-up method. So we just, for this to get a, we cover up s here, and we replace the s's in what's left of this expression with 0, because this is s minus 0. So we're going to get 125 over 0 plus 7 halves times 0 plus a half. Now, this denominator is s minus 7 halves. So we cover up s plus 7 halves and replace s in what's left with minus 7 halves. So we put minus 7 halves in for this s. We ignore this is covered up, and we put minus 7 halves in here. Minus 7 halves plus 1 half is minus 6 halves, which is minus 3. Finally, to get c, the denominator is s minus a half, so we cover up s plus a half and replace s with minus a half. So we get 125 over minus a half times minus a half plus 7 halves. That's 6 halves, which is plus 3. So to get back to this one here, we could take the fraction that's on top, multiply above and below by 4. 4 times 125 is 500, and we've 7 underneath, so then we multiply above and below by 7 and we get this here. As for this one, we multiplied this fraction on top above and below by 2, so we have 250 over plus 21, and we take the 21 into the s plus 7 halves. Here we multiply above and below by 2, so we have 250 over minus 3. We can write it like this. So we get the inverse transform of each of these, and you know, they've got the same form as these here. The inverse transform of 1 over s is 1. The inverse transform of 1 over s plus a half is e to the minus a half t, and for the last term the inverse transform is e to the minus 7 halves t, and we just have to stick in the constants in front. We can see that as t gets larger and larger, e to the minus t over 2 and e to the minus 7t over 2 will go to 0. Both of these terms will go to 0. So I1 is approaching a steady state value of 500 over 7, and I2 is approaching that same value of 500 over 7 as t tends towards infinity.